Hello, my name is Brian Butner. We'll be discussing the 3 Mile Island incident today. 3 Mile accident, apologize for that. We're going to talk a little bit about the early development of nuclear power, the requirements that were set, standards that were used, some of the plant design, and then we'll touch on the event. I think what's really important to take out of this event is you find that America didn't understand nuclear power. Because they didn't understand nuclear power, this accident, well, it was an accident, was minimal to the radiation exposure to the surrounding public due to some of the plant design. The design itself did what it was supposed to do. There were some issues, as we'll touch on, but really, people not understanding what happened at 3 Mile Island and not understanding radiological accidents caused public panic, which in turn prevented government from allowing nuclear power to continue on in the development. This slowed the nuclear power generation for electricity within the United States. Doing this allowed other industries such as coal, fossil fuel type products to move on and become a more dominant figure in the United States. This has led to the increase in greenhouse gases, has caused the global warming, some have said. So we will see, just when we talk here, we'll talk about the accident itself and how it became what it was. I hope you enjoy this lecture. In the early 1950s, late 1940s, I guess you could say, is when nuclear power started to take a foothold. The United States Congress decided that, hey, we need to get involved in this regulation before it gets out of control. So in 1946, they developed the Atomic Energy Act, and then again, retooled that same act and did the Atomic Energy Act of 1954. This really paved the way for nuclear power to start the movement through the United States. The Atomic Energy Commission, which was developed from the Atomic Energy Act of 1954, was responsible for regulation of power plants. They were to keep the public safe as the industry grew, minimizing industry requirements, allowing them to move forward with the process without too much red tape. 1957, the first plant in the United States came online in Shippingport Atomic Power Station. This was the first time power was generated for commercial use. Once this plant came online, the Atomic Energy Commission realized that they needed to have a more stringent requirement. So they decided that licenses need to be granted to plants at this time before they could be constructed. These licenses, to get these, they had to outline the procedures to handle radiological casualties. This was the concern that everyone had for the environment and public safety, people living near these facilities. This was partially because people didn't understand nuclear power, they didn't understand the effects, they didn't understand what radiation doses they would receive, none of these things. So none of these policies, when they were developed, were based on any operational experience at the beginning. Then in 1960, there was the Dresden nuclear power station. This came online. This was the first fully privately funded plant. In the mid-1960s, as the power continued to develop, the Atomic Energy Commission came under some scrutiny from Congress and others about their lack of regulation regarding radiation protection, reactor safety, and environmental protection. They were just not set up to take the large volume of plants that were coming online at that time. The technology and the pace of development was very rapid. Then in 1973, America was put in economic turmoil due to the oil embargo put on by OPEC. This really hurt the economy and made Americans realize they were too dependent on foreign oil to continue on going that route. This is when the utility companies really seized the opportunity and moved forward with nuclear power. They requested 41 nuclear power plant licenses in 1 year. This was a record number, and the Atomic Energy Commission was not ready to handle such a large volume. This is when the Energy Reorganization Act of 1974 took place. Due to the Atomic Energy Commission not performing its duties as it was supposed to and losing public trust, they decided to change it, and they created the Nuclear Regulatory Commission. This commission started its operations January 19th, 1975. The goal of this agency was much like the Atomic Energy Commission, just to keep the public safe. And the NRC took this requirement and went forth. And as you'll see as we talk a little bit more in this lecture, in this discussion, we're going to talk a little bit about some of the requirements that the NRC put together. The NRC is still what we use today and has been continually moving forward and progressing in the nuclear power industry. Between 1977 and 1978, the NRC got together and really started to get the policies in place to make sure licensing was done correctly. This is when they developed the Regulatory Guide 1.101 Nuc Reg 0396. These two documents were important in getting the local and federal agencies ready to go. The Regulatory Guide 1.101 just said that the plan should have detailed emergency plans and how to deal with casualties outside the plant within the surrounding areas. This was important and really set some people allowed people, the American public, to feel safe that the NRC was doing the right thing. Then they also went on and put together the New Reg 0396. This was published in 1978, and this gave more guidance to local and state governments for emergency planning. It really addressed both the short-term and long-term exposure that you could receive pathways. So it gave you two planning zones. It gave you a 10-mile planning zone which was the short-term, and a long-term exposure pathway, and this was a 50-mile zone. This just allowed those people to do some analysis on how far the radiation would reach and to make sure they had a policy in place or procedures in place to handle those types of things. This would, being that it was in 1978, was fairly early on and pretty much right before the 3 Mile Island incident. So the local and state authorities did not have the ability to do a lot of training and practice for what the event they were about to feel or have to deal with. So part of this was that if the policies weren't in place before these plants were put online. The other area of concern was operator licensing. Operators were qualified, yes, they were done through the NRC, but the NRC really struggled to get it right. Between 1955 and then through the AEC and then the NRC, they really struggled to get the training programs where they needed to be. They lacked the depth to get the operators to understand the plant. Forrest J. Remick stated, "I doubt there is always full appreciation of the compelling need for competent, well-trained, and retained staff who have professional commitment towards a quality mode of plant operation. what Forrest J. Remick was saying is he was concerned that operators really didn't understand that how the plant worked. They were really focused more on passing their exams to get certified. After the incident, John G. Kemmy was put in charge of doing a commission to investigate what happened by the president. And what he found is that operators lacked the depth of understanding and were not prepared to deal with the resulting casualty they had seen. So as America grew and nuclear power grew, we put these policies in place. They were just a little bit behind. And the operators were really more focused on passing exams than they were on plant knowledge. And understanding the plant knowledge and how to deal with these things is very important, because you can get compounding casualties, which is what ended up happening, as you'll see, and the operators just weren't sure on how to handle or get it right. Three Mile Island was one of the earlier plants that we put in operation. Not the first, there were others that had been in operation. A little bit about the plant design. It was a pressurized water reactor. Pressurized water reactor just means it had a pressurizer, and it used the pressure on top of the pressurizer to maintain the pressure in the primary plant. This allows you to have high temperature water without boiling. It had 38,816 fuel rods. These were broken up into 208 groups and 177 fuel assemblies. A fuel rod is essentially some uranium inside of a cladding stacked on top, and they put a couple fuel rods in each fuel assembly. These are broken up into 208 groups. Control rods were 80% silver, 50% indium, and 5% cadmium. Control rods are used to help control the reactor. When the rods are inserted, they absorb most of the neutrons. This absorption of neutrons places the reactor in a shutdown condition. It's good to have neutron absorbing materials, obviously, to help with the shutdown portion. It also was a borated water reactor. So for this, they use primary water. The primary water circulates through the reactor to help remove the heat. They have a borated water injection system to maintain the boron concentration in the plant. This allows you to control the reactivity. Early in core life, when the fuel has a higher, it's more potent, I guess you would say, it allows, it stays around 2,000 parts per million. As the plant gets older and you start having fuel depletion, they start to lower the ppm concentration. So this helps control reactivity in the core. The actual vessel itself, which houses the core, was a 40-foot high piece of steel with a wall thickness of 8.5 inches. So the vessel itself contains all the rods inside. This is where your uranium, your rods, everything is inside this vessel. As we talked about, the pressurizer is used to maintain the pressure in the plant. The pressurizer for this plant specifically was 42 feet high and maintained pressure around 2,155 pounds per square inch. This is critical, as you'll see when we get into the event, on keeping the plant without having steam inside the reactor. The whole goal is to maintain a high pressure, keep the bubble on top of the pressurizer, and prevent a steam void from forming within the reactor. So as you see, as we get into this, pay attention to when we start talking about the actual casualty itself, and you'll see where this was an issue. It has the steam generators. The steam generators for this plant were 92 feet long. The bottom for the steam generators were below the core inlets, and this is really critical because it allows for natural circulation to be more easily developed within the propulsion plant. So the flow, the hot and cold leg temperatures allow this natural circulation to take place. So if you do lose your reactor coolant pumps, which typically do provide the circulation through the plant, you still have some flow, which will allow core cooling. The other thing you have is on top of this pressurizer, as we talked about earlier, there's some safety valves. It's a pilot-operated relief valve. The pilot-operated relief valve is designed to protect the plant from overpressurization. This particular one lifts at 2,255 pounds per square inch and was supposed to reset at 2,205 pounds per square inch. As we talk again later on, you'll see where this valve caused the issue. Design features and some other problems within the propulsion plant or within their reactor plant prevented them from understanding what was going on. These valves are critical to prevent the overpressurization of the reactor, though, design hydrostatic test pressures and prevent it from rupturing. This same relief valve, inside the containment building, there is a pressurizer relief tank. The pressurizer relief tank accepts the water that comes out of this pilot-operated relief valve, or the safety valve on top of the pressurizer. This relief tank allows the water collection, therefore preventing it from spilling out into the containment building and then later into the environment. This kind of ties in with the radioactive waste system that was in this auxiliary building next to the containment building. This is where they would hold spent fuel and they would hold radioactive water that was discharged from the plant. Usually it's kept with none, but if it does get water, you have to worry about the radioactive monitoring of that issue. The other thing the plant did have radiation monitoring systems. There was some on the top of the containment building. There was a radiation monitor, and then there was some around the surrounding facilities. These were designed to measure if there was a release of radiation to alert the operators and others of issues. 3 Mile Island had the design plant safety required to keep the plant from meltdown or catastrophic event. Couple systems it had the automatic scram feature, which is basically the insertion of all control rods. This allows to add a lot of negative reactivity all at once, placing the reactor in a shutdown condition. Reactors, though, still will generate decay heat. This decay heat will continue to increase the temperature of water even after the rods go in. So there's a couple systems, water systems, that allow to maintain this cooling of the primary coolant. First of all, you have the emergency cooling system. Emergency cooling system is high pressure injection pumps, in this case, that pump 1,000 gallons per minute of borated water into the plant. This is strictly designed for loss of coolant. If the plant starts to lose water for some reason, a pipe rupture, a relief valve lifting, which is what happened in this case, this allows the water to be pumped in at 1,000 gallons per minute, keeping the core covered with water, which is essential to keeping the plant safe and preventing meltdown. The other feature that this plant had was the auxiliary feedwater pumps. Auxiliary feedwater pumps provide secondary water to the steam generators, which we discussed earlier. This water is used to provide a heat sink, so then water circulates through either via natural circulation or the reactor coolant pumps through the steam generators. This feed water comes in at a lower temperature and cools the primary coolant, allowing to keep the temperature of the primary down. When the feed pumps are lost, which again you'll see when we get to the event, these two systems, the feed water and auxiliary feed water systems, had a huge role in causing part of this casualty. But the auxiliary feed water pumps are an emergency, a backup feed water source to the generator. Providing this feed water helps with the decay heat removal. The feed water pumps let's back up a second. The emergency cooling system pumps were housed in the auxiliary building that was discussed earlier. The auxiliary feed water pumps were housed in the turbine building, which is where most of the secondary side of the water or systems were housed. This is where the turbines were and the other auxiliary functions, secondary side. Here I've provided a quick diagram of the building. As you can see, there were three different buildings. You have a reactor building, the auxiliary building, and the turbine building. The reactor building, called the containment structure, has the reactor, the pressurizer, the steam generator, the pilot operator relief valve, and the drain tank, some of the things we talked about earlier. This is also, you can see here, if you look closely, you can see where the steam generator is lower, like we talked about, to provide that heat sink and that natural circulation of cooling. In the turbine building, you can see the auxiliary feed water pumps. The auxiliary feed water pumps are what we talked about, providing the feed water along with the main feed pumps to provide the decay heat removal of the primary. This was all housed in the turbine building. On the other side, you have the auxiliary building. The auxiliary building is where the radioactive waste tanks were. You can see the high pressure injection pump. The high pressure injection pump is your emergency cooling system. So this is how it all kind of ties together. You can see the three things, the three different buildings, and the portions of what we talked about earlier and where they were in relation. So when we talk about the event, you kind of have a basic understanding of what the plant looked like. The event that took place at 3 Mile Island, as we talked about earlier, had a series of obviously things causing the problem. First of all, the plant, when it was brought online, the first 3 months it had several issues through the production phase and the testing phase. During the first 3 months, the plant was shut down actually for 71% of the time, and it had a 40% failure rate of testing. Many of the issues they ran into are some of the same issues that helped cause the accident. First of all, improper maintenance. Days before the event, there was maintenance performed on the auxiliary feed water system. During this maintenance, there was a lack of control over the valve lineup, and this caused a valve to be left out of position, a block valve as you would call, to prevent, so when the aux feed pumps did start up as required, there was no water flowing to the steam generators due to this block valve being shut. This valve being shut, the workers had no indication that this valve was shut. So there was some lack of control getting into the maintenance. Improper maintenance was being performed at the time of the event. During the event, they were working prior to the event, the workers were trying to clear some resin from a polishing unit. They used an air system. They hooked up the wrong air system, which was at a lower pressure than the water, allowing water to flow into the air lines. This instrument air line that was incorrectly hooked up filled with water and slammed shut automatic valves due to the pressure. This pressure and the shutting of these automatic valves eventually led to the stoppage of main feed being flowed to the plant. So then when the aux feed water pumps tried to start up, they started, but the valve, as we discussed, was shut. So you have zero flow to the steam generators. So now the event actually occurred, it started about 4 a.m., March 28th, 1979. At the time, the plant was operating 97% power and had 4 operators in charge of the plant. There were 2 control room operators who were monitoring the panels. There was 1 supervisor who was in charge of both TMI 3 Mile Island's 1 and 2 plants. And then you had another supervisor who was down working on this maintenance on this polishing unit we talked about there just a second ago. So once the event happened, feed water, just a quick timeline. So feed water was tripped offline. Within 2 minutes, temperature in the primary rose excessively. This increase in temperature caused a rise in water, expansion in water, so the level in the pressurizer increased. And then this, in turn, compressed the bubble at the top of the pressurizer. This bubble being compressed raised the pressure. It got to the set point of 2,255 pounds, lifting that primary relief valve we discussed earlier. The pressure continued to rise. We'll back up a second. When that relief valve lifted, obviously the water from the relief valve went to the relief tank. The pressure continued to rise until it got to 2,345 pounds. When it got to this point, the reactor automatically scrammed as it was designed to do. This added that negative reactivity that needed to happen. Unfortunately, as pressure came down, the primary pilot operated relief valve failed to reseat. So water continued to flow from the core and continued to lower plant pressure. Pressure got to a point at which the operators had to secure the reactor coolant pumps due to the steam, or because of vibrations. This was caused due to cavitation in the pumps due to the lower pressures. Pressure eventually, due to this, got to the saturation pressure in the core and allowed steam formation to take place. So the steam formation in the core forces the water back into the pressurizer and gives indication as though the pressurizer is refilling with water. Unfortunately, this is a bad indication to the operators. They did not realize at this time that the relief valve was still open and was lowering pressure. Eventually, the steam formation produced the heat transfer across the core. It was estimated that the temperature got to 1,077 degrees Celsius. Temperatures got to a point where the zircaloy cladding around the fuel melted, and this is what released the heavy or the highly radioactive particles back into the plant. Some of the other stuff that happened as we were pumping this water into the relief tank, the relief tank could only hold so much. The relief tank eventually overflowed water into the auxiliary building. It also ruptured a disc inside the containment building, and this allowed the temperatures and pressures to build up inside the containment building, also producing or releasing hydrogen. So this was kind of the build up to the event. Obviously the big problems were auxiliary feed pumps not going and giving water to the steam generators, and the pilot operator relief valve sticking open and the operators not understanding why. And we'll talk a little bit about how they didn't, why they didn't recognize that, and then some of the mistakes they made combating this casualty and why they got to the point they were at. So when the event occurred, the operators got numerous alarms. One of the reports you'll read or you can find out there says that they got over 100 alarms at one time. This was very confusing to the operators and led them down numerous paths that it was hard to decipher for them which ones were the important ones. The operators did take the quick actions to counter the tripping of a turbine and the scram. Unfortunately, when that stuck open relief valve occurred, the operators didn't recognize it. And they didn't recognize it because the downstream temperature monitor, which is installed to give you an alarm that it had relifted, it would, it had been in for a long time. It had spurious alarms on it, or frequently had issues with it. So the operators, well, they knew the stuck open relief valve did lift. They assumed the valve had reseated and the casualty was under control. They did not think this valve was stuck open. So when a couple mistakes the operators made themselves is when the stuck open relief valve occurred, they had all kinds of indications they could have used. First of all, they should have noticed lowering pressure and taken actions for the stuck open relief valve. Instead, what the operators were focused on was originally the water level in the pressurizer. So when the casualty first happened, let's step back just a second. When the casualty first happened, the steam generator had water still in there. So the plant scrams and the steam generator is still removing heat. Well, as that's happening, the pressurizer level starts to fall. The operators correctly start pumping in water. However, the water coming in was quicker than the water leaving. So pressurizer level rose and the operators thought things were under control. But eventually the steam generator did run out of water and caused the heat up and pressurizer level to continue to rise, which again caused the operators to determine they don't need the high pressure injection pumps, even though level dropped or pressure dropped. So they secured those pumps also. Some of the other indications they failed to get was as the water was leaving and going into the pressurizer or the pilot operated relief valve relief tank, it overflowed into the containment building and the rupture disc ruptured on the tank. This caused temperatures and pressures to increase within the containment building. The operators had a great chance to understand and find what was going on at this point, but failed to realize it, causing them to take actions to start more fans and not worry about the temperatures. So if the operators would have correctly diagnosed the relief valve and correctly diagnosed the pressurizer level changes, they potentially could have caused or would have left the high pressure injection pumps online. They would have been able to isolate the primary relief valve correctly to prevent the release of water, could have kept the core covered, and could have kept the level up. And this would have been crucial to the overall combating of the casualty. So as we tie it all up here for this section, we're going to go back just real quick. We had the poor certification of plants. This is what led to the event in the first place. The poor certification of plants was the start of how you got to this point, partially because local and federal authorities were not on the same playing field and didn't have enough practice or experience in handling these type of casualties. The other thing was improper maintenance practices were in place throughout propulsion plants, or throughout the reactor plants. So they weren't controlling the way maintenance is done. They weren't using OQE, objective quality evidence, and they weren't using good QA practices. Another issue was deficient operator training and qualifications. As we discussed, operators were not familiar with how to actually operate plants and were focused too much on passing examinations. They didn't really have the grasp or the understanding needed to handle major casualties as they were confronted with. And then, as you'll talk about and you'll hear more of in future discussions, the effect on future nuclear power energy production was impacted by the American public's perception and fear of nuclear power. partially because they were left in the dark when it came to what exactly happened at 3 Mile Island. There was a lot of misunderstanding, a lot of numbers thrown out, a lot of data thrown out that people didn't understand, which caused fear, which caused people not to want these plants around, and this affected nuclear power movement, and it also affected overall the environment in the United States and throughout the world. So I appreciate you for listening to the lecture. I hope you got some knowledge out of it. Again, my name is Brian Butner. I hope you guys all enjoyed this. Thank you.